So as Melissa had pointed out, that our case here was really trying to look at the most conservative way that we could look at how one would see the economics of this. And what we think is that there's a fairly solid case that can be made for making these types of transitions. But we're the eggheads. When you see this actually play out in the real world, that's of course when you sit up and take a look at it in a whole new way. So again, we picked Village Solars because it was there, and we knew how it was being designed. We knew the basic outline of its building structures. But what we found as we continued our discussions, as we reached out to those involved in the project, phase 1 of the project was already under construction. These A, B, and C's, these are ones that are going to be occupied in the very near future. They're going to be fed by the natural gas system that these were originally designed with. What they are now, though, exploring in phase 2, these buildings D and E here, is that they're actually looking to convert these to an air source heat pump design. They had to work with NYSEG to ensure that there was sufficient electrical supply. And actually, the architect for the site is here today, and we can talk more about exactly what drove those choices. But it was in large part other developers that had air source heat pumps, had good experience with them, had good relations with them, and they decided to look at them for this phase 2. The remainder of these buildings are the rest of the phases 3 through 5. So they're looking at air source heat pumps for D and E. One of the questions, of course, that would come up with is this is a fairly dense development with lots of area already taken up. So the question is, could they look at ground source heat pumps? Many people will wonder whether there's even enough space for them. What we looked at is if they wanted to go with ground source heat pumps in future phases, there is more than enough space underneath their parking lots for those well fields to be drilled. So these yellow boxes represent the size of the well fields that would be needed, for instance, to meet the needs of those different apartment complexes, assuming that they were drilled to similar characteristics as the system that SUNY Cortland has on our campus that we'll talk about here in a little bit. So there's almost always more space than people realize because the amount of parking that goes with commercial buildings is generally quite a lot of real estate. So drilling under the parking lots would give them enough space that they could look not only at the air source but also at the ground source heat pumps if they would wish. So what we wanted to look at next was to see what are these implications if they were to take this fairly large development and move completely away from natural gas for the remainder of those phases 2 through 5. So you may have seen in the paper a few days ago, NYSEG talking about the need for new natural gas supply in our area so that new customers could be met. So one of our questions was, how much new demand could you meet if you took a very large development like this and pulled it out of the queue if it was one of those projects that was already being considered as locked into natural gas? So if you took all of those phases 2 through 5 for the system, for the Village Solars, and you assumed that they switched away from natural gas to either air or ground source heat pumps, the amount of natural gas that they would save would be equivalent to about 100,000 square feet of new commercial space, other types of office or lab space. That's a large number, and that alone is a fairly sizable amount of new development. But you could stretch that quite a bit if, in addition, you made the new commercial development with a smarter envelope. So if instead of building your new commercial space that was using this displaced natural gas with just conventional systems, you built it with a more efficient envelope itself, you could more than double that to about 220,000 square feet. And that's a fairly big number. So one of the big questions for us is, how much capacity is there in the queue that NYSEG is looking at in terms of its natural gas demands going forward? How much of that could realistically be converted and pulled out in a reasonable time frame so that the amount of gas displaced would allow these new customers who really do need natural gas for high process heat or some other types of unique uses to be able to get access to it? Okay. So the other question we ask is, we always want to know what the downstream effects are. We're displacing natural gas, but we're increasing electric demand. So the question was, how much are we increasing that electric demand? So if you look at our peak load on these buildings, again, assuming all of those phases 2 through 5 were converted over to air or ground source heat pumps, you would need about 135 kilowatts of new peak demand capacity in order to supply those on that coldest day of the winter. That number doesn't mean a lot to those not steeped in electrical systems, so we compared it to the average electric demand in Tompkins County, and that would represent about a 0.2% increase in our average electric demand. So not 2%, but 0.2%. So it's a modest increase in the overall electric demand. And in fact, it's actually even better than that number would appear, because this new peak demand is occurring in the wintertime. Our current electrical system is designed and sized to meet the summer peak demand, which is higher than the winter demand. And so when we looked at that imbalance, the amount by which our system is oversized because of the high summer peak demand, what we found is in 2015, the expected peak is about 310,000 kilowatts more in the summer than it is in the winter in our particular region, in our load zone. And so if you compare that to what village solars would need, it's about 2,300 times less than that existing peak demand. And if you project forward to 2024, and this is assuming that the Cayuga power plant was shut down, the independent system operator who these numbers came from assumes that the plant will be shut down in 2017 because no firm conclusions have been made. What you find is that our summer demand in balance with winter will actually increase rather than decrease. That will have almost 375,000 extra kilowatts in the winter than we need for the summer peak demand. So there's quite a bit of existing electrical infrastructure that could be used to power these, and this would not provide a particularly big strain on our system. We also wanted to know what are the implications for this investment in terms of the job growth potential. So smarter buildings are employing a larger number of people across a larger number of industries. So instead of a single natural gas system being put in, you're now paying for the extra insulation, the air sealing, the heat recovery vehicles. You're paying for the specialized HVAC systems, which might involve drillers. So there's a lot of different hands that become involved. And so when we looked at what those extra investments were for those 138 units, the remaining Village Solar's apartment complexes, what we found was that it would generate between $135,000 and $160,000 in local revenue. So this is the actual fraction that stays local, not the amount that you pay to some contractor who's buying their heat pumps from outside of our area. This much would be recycled through our local economy, through the salaries and other local supplies. And if you use typical numbers, that would come out to about 5 to 6 additional jobs that would be required on the Village Solar's project compared to what you would get with just a conventional natural gas system. So not only are we displacing gas demand that can be used for other types of economic development, but you are investing in a greener system that has a larger amount of local revenue and local job creation as well.
But in the model that you just described, not that I'm opposed to this because I built green homes and I think it all makes good sense, but the model that you described is misleading. All of these efforts that create this additional revenue one time, and these additional jobs one time, will reduce future revenue and future jobs because it's a superior construction and longer lasting equipment. So I would find it challenging to really push this particular case because green construction has tremendous benefits on every level. More responsible use of energy is very important to this country. But I don't see how you can really propose it's a job creator because it's a job reducer over the decades that we're talking about.
All I would say is that that would only be the case if we were nearing a saturation point with green construction. That we're talking about having to completely overhaul our entire built infrastructure if we're going to really achieve these kind of 80% reductions in greenhouse gases. So this is not something that you're going to do once. You're not going to do the Village Solars project and then stop. These numbers are for that particular project, but if we really were serious about trying to find a pathway to that 80% reduction, we would need a wholly new way of thinking about how we're going to incentivize and encourage this type of green building. And you're right, these buildings will require less maintenance down the road. They do buy less energy, but some of that energy is going to come locally, so it's going to be supporting things like solar development rather than simply shipping money to Exxon and some of the other oil and gas companies that are already outside our region. So I think economically, we have a number of decades of job growth potential here. When we're talking 2050 to 2100, I think that becomes a different question. But in my mind, if we don't get to 2050, if we don't meet those 80% reductions, we can't get our hands around the climate problem, we will make all of these other problems of economic development and inequality and other things so much more severe that they'll be much, much harder to fix.
Tompkins County has spent a lot of time looking at various life cycle costs and benefits more county-wide. And we have an that's a scary amount of aging infrastructure. So if we weren't shipping that money to purchase the gas and the oil off to Texas and Wyoming, we could employ an awful lot of people here for decades, making sure that we come back up to par. And boy, we're in good shape compared to most localities, which is a even scarier thought. So neighboring counties immediately adjacent are in even worse shape.
And the energy transition is also multi-tiered, that as one set begins to mature, you begin to see new avenues for this kind of development. So the electric car infrastructure, for instance, just is almost non-existent in our area, but that's a big area that's going to have to be fixed as the transportation system begins to put more EVs into the marketplace, and as we need those for vehicle-to-grid questions as the renewables edge up. So these technologies are progressive, and so you don't run out of things for these new types of skill sets to do.
My understanding of the electric grid is that the efficiency is pretty poor, and you actually lose quite a bit in just the transmission of electricity through the grid. So, presumably during the day when you're producing a lot of PV, solar electricity, that's when you don't need it necessarily for your residential areas, that's getting put into the grid, and the excess is getting put into the grid, and then say at nighttime when you need it for heating, especially in the wintertime, you're pulling it from the grid. So that back and forth, how much have you guys projected how much you're losing just in transmission back and forth? And is that...
We have looked, all of the numbers that we show here are the on-site energy use. We have looked at what the total system energy use is in terms of fossil fuels. The big losses are not through the transmission system. Those losses are only about 2 to 3%. The bigger losses are in the distribution. The last mile is where much of your loss in the electric system is coming from, because the transmission system is at high voltage, so you have very, very low losses. That last mile to the house, when you're stepped down to much lower voltages, the distribution losses can be more substantial. The solar, though, is actually a net benefit for our system the way it's currently structured, and as we begin to think more cleverly about storage and some of these other things as solar increases, because there actually you are able to shave off your peak demand, which is occurring generally during the daytime. And so being able to shuffle those electrons around through the distribution grid, my house is producing more than I need, so it feeds my neighbor, and then my neighbor, right, it feeds through the distribution system. And that can shave off the need to start up a natural gas peaker plant somewhere else that's running very inefficiently. So it gets very complicated when you want to look at that whole life cycle piece, but the renewables are having multiple positive benefits. And it's one of the things that Melissa didn't have time to talk about, but the question of what is the value of solar on the grid. And it comes in large part from some of these efficiencies that you gain rather than inefficiencies.